guys, this video is going to look at Walding chapter 21 through the 2-star questions. We'll try to get through them all, however if we can't we'll split it into 2 videos, so let's get started. Question 20. An oil droplet experiences an electrostatic force of 5.6 times 10 to the negative 4 newtons when placed into a uniform electric field of 4,000 volts per meter. What is the magnitude of the oil droplet's charge? Okay, let's have a look. So we have here force equals 5.6 times 10 to the negative 14 newtons. We have that the electric field, its uniform, is equal to 4,000 volts per meter, and we are asked what is the charge. Now we do have an equation that links these together, so let's test that out first. I am kind of curious about this unit. I'm not 100% certain if force per coulomb is still the same unit as volts per meter, but let's see what happens. So we know that electric field is defined as force over charge. We'll rearrange that to get charge, so charge will equal force over electric field. Let's substitute that 5.6 times 10 to the negative 14 divided by 4,000. And if we slap that on our calculator, 5.6 to the negative 14 divided by 4,000 gives me 1.4 times 10 to the negative 17 coulombs. And if we take a look in our answers for question 20, we get that it should be 1.4 times 10 to the negative 17. Okay, so I guess volts per meter is the same unit as newtons per coulomb. So we could write that as an established fact then. Volts per meter squared is equivalent to newtons per coulomb. Alright, let's move on. Question 21. Now I've had a few emails about this question, and the problem is that for the grade 11s at this point in time, you don't have as much experience with forces and balancing that the year 12s might do. So first off, let's draw what this would look like. The question reads, 2 small metal-coated styrofoam spheres, each of mass 2.8 times 10 to the negative 6 kilograms, are attached to nylon threads 45 centimeters long, hung from a common point. The spheres are charged equally negative, and the angle each supporting sphere makes with the vertical is 16 degrees, and we want to find out the charge. There's a lot of information there. Let's draw what this looks like. So let's imagine that we have, say, a roof of some sort, and from that are hanging 2 metal-coated spheres. They are some distance apart, and the vertical would be here, and the question reads that that is 16 degrees to the vertical. And we want to figure out, well, what's the charge on these two things? They're repelling, so they must have the same negative charge, and they're both making 16 degrees, and they both weigh the same amount of mass, or they have the same amount of mass, so they have the same weight of force. We want to figure that out. I'm going to draw one sphere, so ball, string. Now on this string we want to look at the forces on it. Obviously we have a force due to gravity. Everything has a force due to gravity if it's near a planet or if it's near any object of solid mass. And if we think about this, these two are going to be the same height because they've got the same mass, they're making the same angle, they've got the same amount of charge, so they should be the same height as well. And that means that this one, so this ball here, let's call it ball B, is going to be pushing ball A in that direction. And ball A will be pushing ball B in that direction. So let's write that the force of A on B, the force of B on A. So let's draw that. We're going to have an electric force that way. And while we haven't covered it, it's pretty simple to sort of see. If this ball is not moving, something has to be holding it in place, because we've got a force trying to shove it in that direction. We've got a force that is pulling it in this direction. So something has to be opposite of that. Something has to be pulling it up, something has to be pulling it to the right, and that's coming from the string. We have here along the string a force of tension. Now we don't need to solve for tension, I just wanted you to see that these things have to add up and be balanced. Now if we have a look at this, we can see that some of our gravity force is acting this way, which means that some of it will act down the string, that's why there's a tension force there, and some of it will act out this way. And the same thing for our electric force, some of it will act down the string, and some of it will act this way. Now, these two forces here, the ones acting down against the string, we don't care about these ones. But this one, we'll call this the force electric on the x and the force gravity on the x. Those two have to be equal but opposite each other. Okay, so we can write the sum force electric x plus force gravity x must equal 0. Right? We could also write one about, oh, well, the force electric in the y, the force gravity in the y, and the force of tension must also equal 0, but we don't really care about that one too much because we're not going to solve force of tension. If we were asking to find tension, then we would care about it, but we don't. Okay, so this is the idea. We've got these two things, that the electric force and the gravitational force, they're going to equal 0, which means then that force electric x must equal the opposite of force gravity x. Okay, so let's go back to our question and see what actually information we're being given. We've told the mass, so that's important. Mass equals 2.8 times 10 to the negative 6 kilograms. And remember, if we have a mass, we can work out the force of gravity acting on it. And we're told that these threads are 45 centimeters. And it's weird that that's done that. Let's rub that out. There we go. And let's see what else we've got in here. That looks to be all. So let's look at our two equations here and see if that will help guide us through what we want to find. So force of gravity means I need to have the mass of the object and I need to have the acceleration due to gravity. Now the mass of the object we've been given, good. Acceleration due to gravity, well, that's a known constant, so that's good. We can solve for that half of the equation. The electric force, well, our electric force equation, remember, is Coulomb's constant, Q1, Q2 divided by the distance squared between the two. So we need to figure out, well, Q1 and Q2 are going to be the same, so we can rub that out and just make it Q squared. Kc is a constant, we can do that. We've got to figure out what d squared is. So let's rearrange this for a second. Q squared equals minus mass, acceleration due to gravity, distance squared, and then that's going to divide by Kc. If we can put all those things together, we're going to have an answer here. So, mass we've got, acceleration we know. Remember, acceleration due to gravity equals 9.81. We need to know the distance between these two. Right? And we actually need to know, what we need in the x, we actually need how much is in the x direction. We haven't worked that out either. I do apologise for that. And we are going to need a bit of an angle working over here. So I'm actually going to get rid of this because this is not going to be the full formula we need to use. We do need to use some angles in here. Alright, let's get into the actual mathy part. I'm going to redraw my picture a bit larger. Okay, I know that I've got a force of tension, and that is 16 degrees. I have a force due to gravity, and some of my gravity goes down here, and some of my gravity goes down here. Let's just do gravity for now. And my question would be, well, what is this angle in here? And we can see, well, this is a straight line. We haven't changed that. That's 16 degrees to the vertical. That's vertical, so that has to be 16 degrees as well. So that means, since we want to figure out that x value for gravity there, we have a nice right angled triangle in here, which tells us then I've got to use a bit of trigonometry. So I'll make that a bit bigger. Just draw that on the side. Here's FGX, here's FG, and that is 16 degrees in there. We can see here we've got the opposite angle, opposite side to the angle, so we're going to use our sine ratio. So the sine of 16 equals our opposite over our adjacent, and Fg in this case is going to equal just mass times 9.81 because it's acting straight down. And if we chuck that in, we will get that Fgx equals 2.8? 2.8, yes, times 10 to the negative 6 times 9.81, and then that's going to be times the sine of 16. Okay, so what I've done there is I've made the substitution for Fg here and rearranged it in one step. Okay, pause it for a second if you need to reponder that for a moment. And if we chuck all that in, we will get an answer of 2.8 times 10 to the negative 6 times 9.81 times the sine of 16, and that gives us around 7.57 times 10 to the negative 6 newtons. Okay, so that equals my amount of gravity pulling me down here, which is going to equal then the amount of electric force pushing up this way. Now let's go back to this picture for a second. We know that the electric force, the total electric force, is out that way. We want to know the electric force in the x direction, and we need to know then, well, what is this angle going to be here? Now, the good thing is, well, we've set this up as this is going to be a right angle. Gravity was acting straight down, the electric force was pushing straight away from it, which tells us then that has to be a right angle there. Also because that has to be a right angle there. So now if we know that that's going to be 16 degrees, then that's going to be the complement, which will give us 74 degrees in there. So that angle gives us 74 degrees. Let's redraw this force triangle just to make it a bit clearer to see. We have force electric in the y, force electric in the x, and this is the one we care about, and that's 74 degrees. Okay, so looking at that, we can see that we're going to need the sine angle again. In this case, it's a sine of 74 rather than the sine of 16. So let's write that out, that Fe, also the sine of 74 equals opposite over adjacent, Fe of x over f of e. The thing is, we know Fe of x, it's going to equal this, so we need to solve for Fe. And we see that Fe will equal Fex over sine of 74, which equals Fgx, or the size of Fgx. I'm kind of ignoring the negative there because I only really care about the size of this actual thing, over the sine of 74, which equals 7.57 times 10 to the negative 6 over sine 74, which equals 7.57, 10 to the power of negative 6 divided by the sine of 74 degrees gives us an answer of 7.87 times 10 to the negative 6 newtons. So that's the total force being felt by this particle. And if we think about the equation, we know that force electric equals Kc. The charges are the same, so I'm just going to do a Q squared, because if Q1 and Q2 are the same thing, it'll just be Q squared, and the distance between the two. And you might be going, well, we don't know the distance between the two charges. And for this, I'm going to go back to my triangle right at the start and say, well, look, this is a nice right-angled triangle here. And so if I can work out this side, I just need to double it, and I'm going to have the distance between the two. So let's draw that up. 0.45, we want it in meters, and that's 16 degrees, and we don't know what that is. Again, there's another sine ratio. So sine of opposite over hypotenuse, we want to solve for opposite. So that means x is going to equal 0.45 sine 16. Really recommend you pause the video and work that out to see how I got to that. Sine 16 gives us 0.124. So therefore, d equals 0.248 because it's this times 2. Remember, we just worked out half, put the other half over here. So now we're at a point where we can rearrange this. So q squared is going to equal fe d squared over kc. Q squared is going to equal, let's see, our force is 7.87 times 10 to the negative 6 times 0.248 squared divided by 8.99 times 10 to the positive 9, sorry. 10 to the positive 9. So 7.87 exponential 6 times 0.248 squared divided by 8.99 power of 9. So that gives us that q squared equals 5.38 times 10 to the negative 17. So square root the answer. We get that q is equal to 7.3 times 10 to the negative 9 newtons, and the answer at the back is 7 times 10 to the negative 9 newtons. They've obviously rounded off a bit, and if we have a look at that, I mean, we've got a lot of calculations, so eventually you would have to round off a little bit. That's a really tricky question. Okay, there's a lot of geometry in there and a little bit of understanding about forces. That's not really a year 11 style question at this point in time, but for year 12s this would be the sort of question that I expect you to be able to solve. Okay, let's keep going. 22. A metal sphere carries a charge of 20 microcoulombs. If it has a diameter of 20 centimeters, what will be the potential at its surface? So, when we have these sort of things, a metal sphere, and Q equals 20 microcoulombs. Sorry, since it's a charge of just one object, we should just go capital Q. And we know that it has a diameter of 0.2 meters. Therefore, radius equals 0.1 meters. Now you got to be careful with this because I believe the formula that we're using uses the symbol D. What we want, we're going to use R because it's the radius of a sphere, and we want from the center to the edge. And the question is, what is the potential, electric potential coming to the surface? Yes, what is the potential at its surface? Okay, now if you scroll up through your text, you will flip back through the pages of the text. I'm trying to find the formula to point out to you. There it goes. So the potential from a point from infinity is equal to kq over d. Okay? Now d in this case means the distance from it, from where you're bringing it to compared to where you want to get to. So we're bringing it to the surface, which is 10 centimeters away from the midpoint. So we're going to use this number of 0.1, not this number of 0.2. That's why this is a two-star question, because you might go, D for diameter, and then go and use D for distance. So voltage equals kcq over d, or in this case we'll use R, 8.99 times 10 to the 9 times 20 times 10 to the negative 6 divided by 0.1. And remember, convert those microcoulombs into metric prefix, or get them out of the metric prefixes, times 20 to the negative 6 divided by 0.1. So that will give us 1.8 times 10 to the 6 volts. And if we go to 21, question 22, 1.8 times 10 to the 6 volts. So what this is really asking is, well, let's say that we're all the way over here at infinity and we come all the way to this point. Compared to being at the center, what is the potential difference? when we're talking about a metal sphere, we assume all charges at the surface, and we're comparing with there versus in the center there. 23 was a one-star question that's in that other video. 24. Two metal plates are oppositely charged and are separated by a distance of 4.5 millimeters in a vacuum. A voltage of 520 volts is connected across the plates with the top plate positive. What is the strength of the electric field between the plates? The force on a test charge having an excess of 50 electrons on a place between the plates. Okay, let's draw this. We're going to have top and bottom. They've said that top plate is positive, so that means the bottom must be negative, and that voltage equals 520 volts. Now the distance between the two is going to equal 4.5 millimeters. 4.5 millimeters. So distance equals 4.5 times 10 to the negative 3 meters. And we are asked for A, what is the strength of the electric field? So E equals, I don't know. Well, voltage just equals E times D, as I recollect. So again, if we scroll back through our where is it? Our textbook to look for that, we see that if we the work is done is equal to QED, therefore the voltage equals electric field times distance. So therefore electric field must equal voltage over distance. And you can see that equation on page 458 of your textbook. So we substitute that in, 520 over 4.5 times 10 to the negative 3. Which gives us 1.15, also 1.16 times 10 to the 1, 2, 3, 4, 5, 10 to the 5 volts per meter, or newtons per coulomb. Always good to think about two different units there. We'll double check we're doing that right. They've got 1.2, they've rounded all the way off to 1.2 times 10 to the 5. Okay, second part of this question is that the force on a test charge having an excess of 50 electrons on it placed between the plates. Okay, so it's a uniform field. It's going to have the same electric field everywhere. We want to know what is the force when Q equals 50 electrons. It says in excess of 50 electrons, but they didn't tell us how many in excess, so let's just assume 50. 50 electrons, remember, each electron has a charge, so the charge of one electron equals 1.602 times 10 to the negative 19 coulombs. So the Q of 50, why do I keep doing e to the minus 1, equals, so 1.602 times 10 to the negative 19, multiply that by 50, that should be 8.01 times 10 to the negative 18 coulombs. Now we've got our Q, we've got our E from part A, and so now we can work out F. So the equation E equals F over Q, which means then that F equals EQ equals 1.2 times 10 to the 5 multiplied by 8.01 times 10 to the negative 18. So multiply that by 9.6 times 10 to the negative 13 newtons. And doubling check, 24, 9.6 times 10 to the negative 13. Okay, now the last, remember this is a force, so it needs to be in terms of direction. We're going to put a negative particle. It's got a lot of negatives, but it's just a big negative particle here. Remember, the field goes this direction, in the direction of positive things. but this is a negative thing, so which direction it's going to go? It's going to get pushed away from this negative plate, and it's going to go upwards. So I'm going to write up next to my direction. Do not forget directions. It can cost you marks. It will cost you marks. How many more 2 stars have we got? 25, 26, 27, 30. 30 is a pretty big one. It involves graphing. 20. 27 is pretty trivial. we'll do 25 and then we'll finish there. I don't want to make this video too long. An electron in the gun of a CR tube. So a CR stands for cathode ray tube. It's what we used to make televisions with. If you've got a really old, well, when I say really old, I mean they're still, within the last 20 years, or the last 10 years easily. So it's one of those TVs with the big back on it, so you've got the screen, but then it's very deep in comparison to LCD or plasma TVs where they're very thin because they don't have this technology. And a cathode ray gun or a cathode ray tube is basically a thing that shoots electrons in a pattern across the TV. So it's always, I think it's from the top left corner across, then it goes down a pixel, then it goes all the way across, down a pixel, across, down a pixel, across. If you've ever watched an old television recording, you'll see as you pause it kind of a little bright spot somewhere in the screen where the picture might be half changing because you're not actually seeing a moving picture, you're seeing 30 or so or up to 60 frames every second of still pictures. Okay, so let's have a look. Accelerated by potential. So potential, remember, is given the symbol V. 3.0 times 10 to the 3 volts. 3.0 times 10 to the 3 volts, so 3,000 volts. What is the kinetic energy of the gun in electron volts and joules? We know that Q is equal to 1 electron, which equals 1.602 times 10 to the negative 19. We want to know what is the kinetic energy. Equals I don't know. And we want it in 2 units, electron volts and joules. Second bit is what is the exit speed of the electron from the CR tube gun. Now the first bit, in terms of working out the total kinetic energy of it in joules, that will definitely be something at year 11 you could do. Electron volts are a unit we haven't covered yet, so not a huge drama. I mean, you could find a definition for it pretty quick. I mean, if you go to Google and search joules to electron volts, you'll get a conversion factor and a little app to do it for you straight away, so that's not hard to do. I'll leave that to you to have a look at. Exit speed, though, is going to use the kinetic energy equation that you learned last year in year 10 sciences or in year 11 physics, in terms of kinetic energy equal half mv squared. So let's start off with this and see how we go. Now, we want to know the relationship between energy, volts, and charge. However, we can also say that, what's the word I'm looking for? Kinetic energy is the same thing as giving us some energy. It's getting some work being done to it. Actually, in fact, if you scroll up to page 462 on your text, you will find an example of this. In fact, it gives you a full worked example of this question. So I'll leave you to have a read of that. What we'll find is that work equals Q times V equals 1.602 times 10 to the negative 19 times 3 times 10 to the 3. 1.602 times 10 to the negative 19 times 3,000 gives me 4.8 times 10 to the negative 16 joules. And this will be exactly the same amount of what's what we're looking for? Kinetic energy it'll have as well. Okay, so the next bit is to what is the electron volts. Now, electron volts is kind of nifty in this case, in that an electron volt is the unit of energy if we divide out how many amount of electrons would actually be into it. So if I take the number of joules and I divide it by the number of electrons, I find that, well, I'm just essentially reversing that. So that means the electron volt value will equal 3000, or 3 times 10 to the 3, electron volts. So we find that the amount of work done, the amount of energy given to it, is just equal to the voltage. And that's because this is a very, very small number. This is a much easier number to work with. Okay, the second part of this problem is about finding what the actual velocity is. And the formula we want for that is that kinetic energy equals half mv squared. Now, the mass of an electron is a known constant. Let me see if the previous work example actually had it. Yes, so the mass of an electron equals 9.11 times 10 to the negative 31. Okay, this is something that would be provided to you on exams. It is a known constant of the universe, so it's not something that you would be expected to remember. However, and the kinetic energy is the same thing as the work that has been done. Okay, so in fact, I'm going to put that there. So that means I'm going to have 4.8 times 10 to the negative 16 multiplied by 2 to get the half across, divided by 9.11 times 10 to the negative 31. And that's going to equal v squared. So v squared will equal, sorry, that should be 4.4, that should be 4.8 times 2 divided by 9.11 10 to the power of negative 31, which gives us a very large number of 1.06 times 10 to the 15. So even though this number is a small number, it's a very small amount of joules, this is, like if that has 16 zeros before it, or 15 zeros before it, that has, sorry, 16, that has 31 zeros before it. So it's a billionth of a billionth of a percent, sorry, a millionth of a billionth of a percent of the first value there. Okay, and that equals v squared. So v is just going to equal the square root of that number, which is going to give, oh, that's a huge number, 3.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 7 meters per second. Now, always important when you're dealing with very, very high velocities is to double check this against the speed of light. Now, the speed of light, we give it the symbol c, equals 3 times 10 to the 8. This is about 1/10 the speed of light, and that's what's happening in those old TVs, that they're shooting electrons at 1/10 of the speed of light. The fact that that number isn't bigger than 3 times 10 to the 8 is a good thing, because if it did pass 3 times 10 to the 8, that would tell us that we've really done something wrong with our mathematics. Okay, now I will put questions 26, 27 and 30 in another video, and I will leave you to work 31, 32 and 33 out on your own. Thanks very much, guys. Have a good night. Bye.